morning, sir. Good morning, everyone. In this lesson, we are going to tackle about triple integral. But before that, allow me to introduce the members of this group. Hera Isidro, Rosemary Palma, yours truly, Christine Britannia, Christy Caballero, Mig Enriquez, Cindy Malapitan, Ricky Piroy, Cher Rose Hernani, and Ronald Jade Bourbon. This will be our learning objectives. At the end of the lesson, you will be able to first define the concept of triple integrals, evaluate triple integrals, and sketch the bounded region of the given function to determine the lower and upper limits. Now that we know how to integrate over a two-dimensional region, we need to move on to integrating over a three-dimensional region. We use a double integral to integrate over a two-dimensional region, and so it shouldn't be too surprising that we will use a triple integral to integrate over a three-dimensional region. A triple integral is a three-dimensional extension of the usual integral. It is used to add up infinitely many infinitesimal quantities associated with points in a three-dimensional region. Imagine you want to find the total amount of something in a 3D space, like the total mass of an object. A triple integral helps us do that by breaking the space into tiny pieces, finding the amount in each tiny piece and adding them all up. It's like adding up all the tiny bits to get the total for the whole 3D space. A triple integral is a mathematical concept used in calculus to calculate the sign volume within a three-dimensional region. It involves integrating a function over a region in a three-dimensional space. A triple integral can be written as the triple integral over the region D of the function x, y, and z with respect to the volume element dv, where D is the region defined by the limits specified by E. D is the region of integration and F is the function to be integrated. It starts by simply integrating over the box. B is equal to the quantity of A and B times the quantity of C and D times the quantity of R and S. And take note, class, that when using this notation, we list the X first, okay? And the Y second and the Z third. And the triple integral in this case is the triple integral of function x, y, z over the region B with respect to the volume dv is equal to triple integral of function x, y, z dx, dy, dz, where x runs from a to b, y runs from c to d, and z runs from r to s. And note that we integrated with respect to x first, then y, and finally z here. But in fact, class, there's no reason to the integrals in this order. There are 6 different possible orders to do the integral in, and which order you do the integral in will depend upon the function and the order that you feel will be the easiest. And we will get the same answer regardless of the order, however. Now, to deepen your comprehension of triple integral, my fellow group members will provide an illustrative examples in the presentation. Thank you so much.
Hi everyone. To further understand on how to solve the triple integral, let us consider this first example. We have evaluate the triple integral of 8xyz dv with xyz bounds 2 to 3, 1 to 2, and 0 to 1 respectively. Upon writing those bounds in each integral, we will have the integral from 1 to 2, the integral from 2 to 3, the integral from 0 to 1 of 8xyz dz dx dy. Instead of writing dv, we wrote the dz dx dy because we are using a rectangular coordinates. Now, the first thing that we are going to do is to evaluate first the inside integral, which is the dz given by the example. So upon evaluating or finding the antiderivative of 8xyz with respect to z, we will have 8x v squared over 2 evaluated from 0 to 1. So our new expression will become the integral from 1 to 2 and the integral from 2 to 3 of 8xy times z squared over 2 evaluated from 0 to 1 dx dy. So we can simplify this one by dividing 8 by 2 and our expression will become the integral from 1 to 2 and the integral from 2 to 3 of 4xyz squared evaluated from 0 to 1 dx dy. Upon substituting z with the bounds, so the upper bound minus the lower bound, this will result to 4xy. And then our new expression will become the integral from 1 to 2 and the integral from 2 to 3, 4xy dx dy. Now next is, we are going to evaluate again the inside integral. So upon finding the antiderivative of 4xy with respect to x, this will result to 4x squared over 2 times y. So our new expression will become the integral from 1 to 2 of 4x squared over 2 times y evaluated from 2 to 3 dy. So simplifying that again, 4 divided by 2, this will result to 2x squared times y. So our new expression will become the integral from 1 to 2 of 2x squared times y evaluated from 2 to 3 dy. Then substitute all x variables with the bounds, upper bound minus the lower bound. So we will have the integral from 1 to 2 of 2 times 3 squared, which is the upper bound, minus 2 times 2 squared y, which is the lower bound, then dy. Upon simplifying that, it will result to the integral of, the integral from 1 to 2 of 18y minus 8y dy. So we can subtract 8 from, we can subtract 8y from 18y, which will result to 10y. So our expression will become, our new expression will become the integral from 1 to 2, the integral from 1 to 2, 10y dy. Then we are going to find the compute for the antiderivative of 10y with respect to y, which will result to 10y squared over 2. Then evaluate it with respect to the bounds of y. So we will have 10y squared over 2 evaluated from 1 to 2. Then we can simplify that one. 10y squared over 2 will become 5y squared. And then evaluate it from 1 to 2. And then substitute those bounds. So we have 5 times 2 squared, which is the upper bound, minus 5 times 1 squared, which is the lower bound, which will result to 20 minus 5, and then which will also result to 15. So the answer of this example in evaluating triple integral of 8xyz with xyz bounds 2 to 3, 1 to 2, and 0 to 1 respectively is 15.
We have example number 2. Evaluate the triple integral of the function 2x dv, where E is the region under the plane 2x plus 3y plus z that is equal to 6 that lies in the first octant. Okay, as you can observe in the problem, there is no given bounds. So we have to sketch the function in order to find, in order to determine the lower limit and the upper limit. So before we sketch the regions, we define first what is octant. When we say octa, it means 8 or divided into 8 regions. Okay. Hatagan ta mo og analogy sa 2D dimensional plane natay gitawag og quadrants. First quadrant, second quadrant, third quadrant, and fourth quadrant. Sa 3-dimensional plane, it will be divided into 8 regions na tinatawag nating first octant, second octant, so on and so forth. So, when we say first octant, the x, y, z, kasi 3D man yan, the x, y, z are all positive. So, therefore, x is positive, z is positive, and y is positive. So, sketch natin ang ating function sa first octant according to the condition of the problem. Since this is triple integral, we have 3 differentials here, dz, dy, and dx. The z-axis will serve as the height of our solid. So, the problem tells us that E is the region under the plane 2x plus 3y plus z that is equal to 6. So, we have to manipulate the z in terms of the plane x and y. So, therefore, z is equal to 6 minus 2x minus 3y. And that equation will serve as our upper limit since the problem tells us that E is the region under of that plane. Now, what will be our lower limit? Since it states that the region lies in the first octant, so therefore, the value of z should be positive. What is the lower limit of the set of positive is 0. So therefore, we have the triple integration of the function 2x with respect to z from the lower limit of 0 to the upper limit of 6 minus 2x minus 3y. So we can now simplify the inner integral. So we have the double integration of 2xz evaluated from 0 to 6 minus 2x minus 3y. Then simplify by the rules of substitution. We have the double integral of 2x times the quantity of 6 minus 2x minus 3y, the value of our z, minus 0. And 0 will be disregarded since it affects nothing in the expression. We are now in the double integral, where our differentials will be dy and dx. We can see the intersection of the solid and the xy plane by equating z that is equal to 0. So therefore, our equation will become 0 equals 6 minus 2x minus 3y. Then, manipulate the y in terms of x. So we have 3y that is equal to 6 minus 2x. And finally, we have y equals 2 minus 2x over 3. That will be our equation, that will be our plane in the base of the solid. So by sketching that region, we can see the bounds of y and x. For y, the lower bound will be 0 and the upper bound will be 2 minus 2x over 3. And for x, the lower bound is 0 and the upper bound is x that is equal to 3. Let's go back to the equation. We have the double integration of 12x minus 4x squared minus 6xy dy dx, where y runs from 0 to 2 minus 2x over 3 and x runs from 0 to 3. Then apply the integration rule for the inner integration. So we have the integral of 12xy minus 4x squared y minus 3x y squared evaluated from 0 to 2 minus 2x over 3 with respect to x runs from 0 to 3. By substitution of the upper limit is equal to the integral of 12x times the quantity of 2 minus 2x over 3 minus 4x squared times the quantity of 2 minus 2x over 3 minus 3x times the quantity of 2 minus 2x over 3 squared with respect to x runs from 0 to 3. And expand the expression by applying the PEMDAS rule. We have the integral of 24x minus 8x squared minus 8x squared plus 8x cubed over 3 minus 3x times the quantity of 4 minus 8x over 3 plus 4x squared over 9 with respect to x with a limit of 0 to 3. Then further simplify and combine like terms. We have 24x minus 6x squared plus 8x cubed over 3 minus 12x plus 8x squared minus 4x cubed over 3 with respect to x with a limit of 0 to positive 3. Then we have the integral of 4x cubed over 3 minus 8x squared plus 12x with respect to x with the lower limit of 0 and the upper limit of 3. Then, since that is simplified, we can now apply the rules of integration, the power rule in each term. So we have x raised to 4 over 3 minus 8x cubed over 3 plus 6x squared evaluated from 0 to 3. Then apply the substitution, 3 raised to 4 over 3 minus 8 times the quantity of 3 raised to 3 over 3 plus 6 times the quantity of 3 squared minus 0. Since 0 affects nothing in the equation, therefore by simplifying the fractions, we get the final answer of 9. As you can see, there is no unit involved since we're just evaluating the triple integral. The triple integral is not limited for the rectangular and three-dimensional coordinates. Like the double integral, the triple integral also involves problems that uses the polar and cylindrical coordinates. I think it will be demonstrated in the next example.
For example number 4, evaluate the triple integration of the function square root of 3x squared plus 3z squared dv, where E is the solid bounded by y equals 2x squared plus 2z squared and the plane y equals 8. Here's the sketch of the solid E. The region D in the xy plane can be found by standing in front of this solid, and we can see that D will be a disk in the xy plane. This disk will come from the front of the solid, and we can determine the equation of the disk by setting the elliptic paraboloid and the plane equal. 2x squared plus 2z squared equals 8, so we will divide both sides by 2, and it will be x squared plus z squared equals 4. This region, as well as the integrand, both seems to suggest that we should use something like polar coordinates. However, we are in the xy plane and we've only seen polar coordinates in the xy plane. This is not a problem. We can always translate them over to the xy plane with the following definition. X is equal to r cos theta and z equals r sin theta. Since the region doesn't have y's, we will let z take the place of y in all the formulas. Note that these definitions also lead to the formula x squared plus z squared equals r squared. With this in hand, we can arrive at the limits of the variables that we'll need for this integral. 2x squared plus 2z squared less than or equal to y less than or equal to 8, then 0 is less than or equal to r is less than or equal to 2, then 0 is less than or equal to theta less than or equal to 2 pi. The integral is then the triple integration of the function square root of 3x squared plus 3z squared dv is equal to the triple integration of the function square root of 3x squared plus z squared from lower limit 2x squared plus 2z squared to upper limit of 8 with respect to y. So we have the double integral of y times the square root of 3x squared plus 3z squared evaluated from 2x squared plus 2z squared to 8. Simply, we have the double integral of square root of 3 times the quantity of x squared plus z squared and 8 minus the quantity of 2x squared plus 2z squared dA. Now, since we are going to do the double integral in polar coordinates, let's get everything converted over to the polar coordinates. The integrand is square root of 3 quantity of x squared plus z squared times the quantity of 8 minus quantity of 2x squared plus 2z squared is equal to square root of 3r squared times the quantity of 8 minus 2r squared. Now we have square root of 3r times quantity 8 minus 2r squared, then square root of 3 times quantity of 8 minus 2r squared.
The integral is then the triple integral of square root 3x squared plus 3z squared dv is equal to the upper bounds 8 and lower bound 2x squared plus 2z squared dA. So the new expression will be double integral of square root 3x squared plus 3z squared y from 2x squared to 2z squared to 8 dA. Now, since we are going to do the double integral in the polar coordinates, let's get everything converted over the polar coordinates. The integrand is square root of 3 times quantity of x squared plus z squared times 8 minus the quantity of 2x squared plus 2z squared equals square root of 3r squared times 8 minus 2r squared. There is equal to square root of 3r times the quantity of 8 minus 2r squared. In this case, we just substitute x squared plus z squared to r squared. Then the integral is then triple integrals of square root of 3x squared plus 3z squared dv is equal to double integral of square root of 3x squared plus 3z squared y from 2x squared plus 2z squared to 8 as we integrate it with respect to dy. Then simplifying by substituting all y variables with the lower bound and upper bound, we will have double integral square root of 3x squared plus 3z squared times 8 minus square root of 3x squared plus 3z squared times 2x squared plus 2z squared dA. Then by simplifying, we have double integral 8 minus the quantity of 2x squared plus 2z squared times square root of 3x squared plus 3z squared dA. Since we can factor out the 2 in the expression 2x squared plus 2z squared, then we will have a double integral of 8 minus 2 times the quantity of x squared plus z squared times square root of 3 times the quantity of x squared plus z squared dA. In this part, we also factor out the 3 in the 3x squared plus 3z squared. Earlier, we substitute r squared in the x squared plus z squared. Now we are going to do that also in this part, so we will have double integral 8 minus 2r squared times square root of 3r squared dA. Cancelling the square root of r, we will have a double integral of 8 minus 2r squared times square root of 3r dA. In this part, we can distribute r in the 8r minus 2r squared. So we will have double integral of square root 3 times 8r minus 2r cubed dA. Since we are using a polar coordinates, our expression will become square root of 3 integral 0 to 2 pi integral 0 to 2 8r minus 2r cubed r dr d data. We are going to substitute r in 8r minus 2r cubed. Now we will have square root of 3 integral 0 to 2 pi integral 0 to 2 8r squared minus 2r raised to 4 dr d data. Then we will get the antiderivative with respect to r. We will have square root of 3 integral 0 to 2 pi integral 0 to 2 8r cubed over 3 minus 2r raised to 5 over 5. Evaluated from 0 to 2 d data. We are going to substitute the value of bounds in the r variables. So we will have square root of 3 integral 0 to 2 pi integral 0 to 2 8 times 2 raised to 3 over 3, then minus 2 times 2 raised to 5 over 5 day data. Then upon simplifying, the result will be square root of 3 integral 0 to 2 pi 128 over 15 d data. After that, we are going to get the antiderivative with respect to data. So we will have square root of 3 times 128 over 15 delta evaluated from 0 to 2 pi. Then substitute the bound in all data. We will have square root of 3 times 128 times 2 pi over 15, which will result to 256 square root of 3 pi over 15.
Now, since we are done talking about triple integral, let us proceed to our assignment. But first, please follow the format. In the upper left side, your name. Under to it is Math 24 Calculus 3. And the upper right side, BSed Math 3E. Under to it is Assignment 4. For the instruction, in your one whole sheet of paper, answer the problems and apply the triple integrals in each function. Each of the problem worth 5 points, and this problem will held as your assignment. Supposedly, this assignment would be passed next week. Thank you and goodbye.